Rates of nuclear decay follow first-order kinetics, and that was a topic that we discussed in Chapter 14, so you could go back and look at the Chapter 14 playlist if you wanted. And in Chapter 14, we were generally talking about some reactant A turning into a product where the rate that we were measuring was in concentration units, so the concentration of a dissolved compound per second. And the first order rate law, graphically, we could represent that as the x-axis being time and the natural log of the concentration of A at any time t as the y-axis. And this was found to be a linear relationship, and that really came from calculus, doing dA dt, setting the rate itself equal to the rate constant times A to the first power. So first order kinetics means our power is 1 and that there is only one reactant, and this is probably actually negative since the amount of A we start with is always decreasing. So we did some hocus pocus calculus and algebra on this and could rearrange this equation and come up with the natural log of the concentration of A at any time t is equal to the negative of the rate constant K times the time plus the natural log of the initial concentration. And what we're going to do now is, instead of writing our variable as a concentration unit, we're going to write this as the activity. So the log of the activity at any time t is equal to negative kt plus the natural log of the initial activity. So instead of calling this the rate constant, we'll refer to this as the decay constant because that's the process occurring. And N is the activity, and that's often measured with a Geiger counter. So activity units, the SI unit for that is a becquerel, VQ, which is 1 disintegration per second. And that could be heard if you put a Geiger counter up to a radioactive material. You'd hear tick, 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 lots of, excuse me, ticking going on. Also a Curie, named after Madame Curie, could be an activity unit. So problems that we might see in a textbook may give us the activity measured, perhaps the initial activity measured, and then the final activity measured, and ask us to calculate the length of time required for that nucleus to decay, and that would also depend on the rate constant. But we know that the activity is proportional to the mass. So for example, the more, and that's not the alpha particle, that means proportional to now. So we may see in a word problem, the mass might be given of any radioactive substance. So technically we could put that into this equation, the natural log of the mass at any time t equals negative kt plus the natural log of the initial mass. And I'm going to rearrange this equation and say the natural log of our activity at any time t minus the natural log of the initial activity is equal to negative kt. And if you remember your intermediate algebra, when we have natural logs or base 10 logs, if we can expand or condense a log. So we could rewrite this difference as the natural log of the ratio of the activity at any time t over the initial activity. That would be negative kt. If we solved for the half-life, so half-life of any radioactive substance just depends on what that substance is, so we'll talk about that in a few minutes. But the half-life is when half of the substance is gone. Or that would be the same thing as when half of the substance still remains. And that would be no matter how much material we started with. If we only have half left, then this ratio, excuse me, this dry spring weather is making it difficult for me to talk, but this ratio would be a half. So if we substitute that in, the natural log of 1/2 equals negative kt, and then solve for t, that will be the half-life. So if we solve for t, then we're going to divide both sides by negative k. And when we do that, we'll write t 1/2. If we take the natural log of 0.5, this is going to be negative 0.693 divided by negative k. And there's no reason to have two negative signs in a formula, so these two negative sides cancel, and t 1/2 is equal to 0.693 divided by k. Or I kind of like to have my unknown on the left. T 1/2 is equal to 0.693 divided by the decay constant, which we write as a lowercase k. So in a story problem, we may be given a substance's half-life and be asked to solve for how much of that substance remains after any time t. And if we're not given the rate constant or the decay constant k, but we're given the half-life, we can rearrange this equation and solve for k. So just switch places. K is 0.693 divided by the half-life. So I'm going to list on the next piece of paper the half-lives of a few isotopes. So we could look this up. Uranium-238, its half-life, if I just write that across the top, its half-life is 4.5 billion years, which means it takes a long time for uranium to undergo decay so that only half of the uranium is left. Radiometric dating or carbon dating, that uses the isotope carbon-14. That half-life we know is 5715 years. So carbon dating is good for approximately 50,000 years. And since uranium has such a long half-life, This isotope is often used to date things like rocks, how old rocks are. So if we think about continuing to cut something in half, there's kind of a limit to how many times you can fold a piece of paper in half. So the longer the half-life, the greater the aging process we could use that for. So I'm not sure what that number is. Another isotope that's common that's used for thyroid treatment is iodine-131. And again, I have not been writing the atomic number here, but that is really not necessary because we could always look on the periodic table for that. So the half-life of iodine-131 is about 8 days. Okay. So half-lives are constant for whatever isotope in particular that we happen to be looking at. So for example, we could see a question like, let me rewrite the first order rate equation. So if we have the natural log of the activity at any time t over the initial activity, and again this would be easy to remember because we're ratioing what we have divided by the amount that we started with. So our initial concentration is always in the denominator, equals negative kT. Of course, if we flip this fraction around, we would change that sign, but this is typically the way this equation is written. And also remembering that T1/2, which is the half-life, is 0.693 divided by K. So I'm just going to make up a problem and we'll solve for perhaps how much carbon-14 would be remaining after so many years, depending on how much we start with. So I'll do that example. I'm going to use mass because that's normally what is easiest to measure. If a 25-gram sample of carbon-14, so we might see that symbol written like that. If a 25-gram sample of carbon-14 is, I wouldn't say allowed to decay, because carbon-14, there's not anything that can be done to prevent this type of spontaneous reaction, but is found to decay to, I'll say, 10 grams. Determine the time required to do so. And if we were not given the half-life of carbon-14 in the problem, we would have to go look in the book, but I'll go ahead and write that down. The half-life is 5715 years. So if we look at the information we're given, we are being asked to solve for time. So how much time does it take for that sample to decay so that there are only 10 grams remaining? So if I just plug those values in, the natural log and the initial concentration goes on the bottom, or the initial mass, and the final mass goes in the numerator. So this is 10 grams divided by 20 grams. So our units need to be consistent there. Equals negative KT. The problem did not give us the decay constant, but since we know that this is first order kinetics, the half-life allows us to solve for K, so I probably should have done that first. K is equal to 0.693 divided by the half-life, which is 5715 years. So if we do that division, I'd have to use my phone. I can't find my calculator. So if we take 0.693, divide that by 5715, we get this small number. So I'm going to write 1.21 times 10 to the negative 1, 2, 3, 4. And the units for this would be a 1 over a year, or give myself a little more room. The rate constant is equal to 1.21 times 10 to the negative 4. You might see this unit written as a reciprocal year. Year to the minus 1 is the same as 1 over year. So whatever our decay or our rate constant unit is, depending on the half-life unit, that will be the same unit that our time is. So I'm going to rewrite this equation. I'm actually going to just go ahead and show dividing by negative k on both sides. So if I divide this side by negative, I'm going to put the k value in there, 1.21 times 10 to the minus 4 reciprocal years. So now we have t isolated in the equation. And then we just have to be careful on making sure that we plug numbers in the calculator correctly. So I usually use my TI calculator, so we'll be able to see if this answer makes sense. So if I take the log, and good thing these have parentheses, I'm going to take the log of 10 divided by 25 and close the parentheses, and then divide that by, I'm going to just put this back in decimal form to put it in the calculator, 0.000121, and enter that. You get a negative. That does not sound right. So I think what I'm going to do is redo this and enter my value right here. So let me clear that out. Sorry about that. Take the natural log of, where is that button? And take the natural log of 10 divided by 25, close parentheses, and enter that number. So I knew we couldn't have a negative answer because the log of any fraction less than 1 has to be negative. So now that I've got that number in there, that's my numerator. Now I'm going to divide by a negative 0.000121. I guess I'll close that parenthesis. Oh, I still get, well, oh, I guess we're solving for time. I was thinking we were solving for mass. So I get the same answer, so I guess my calculator knows how to do its order of operations. So t equals 7,573 years. And I can't really do two things at once, talk and think. So that really should make sense. And it does make sense if we consider that half of 25 grams, if our initial amount, or we're going to write that as activity, if our initial activity was, or our initial mass was 25 grams, half of that So after 5715 years, then we would have 12.5 grams remaining. And we have less. The problem said that there were 10 grams remaining, and since its half-life is 5,715 years, that means 12.5 grams would still be remaining. So 10 grams is less than that, meaning that carbon would still continue to decay for a number of years before we got down to 10 grams.